Okay. Okay, good afternoon. We're going to start. I am not Gwendal. Gwendal is done sharing the sessions for today. My name is Cyril Concolato. I work for Netflix, and I'm here to introduce this last session of the day. We're going to talk about low latency streaming. We had already a few presentations tackling this issue this morning. They talked about L3D and Dash and LL Dash. But for this first presentation, we have Keith, who's going to get us back to good old RTP and UDP, right?
Yep.
So take it.
It's 30 years old, and it's still working. And most of the broadcasts are still using MPEG transport stream. Okay. So my name is Keith. I'm the product manager of the IP solution in Nokia. I'm part of the IP network and network infrastructure. Today I'm going to talk about the live streaming. Okay. Nothing to do with VOD. We also do time shift TV, but it's done in the on the client side, local storage, not going up to the network. Okay. I'm going to talk about IP broadcasting distribution over any IP network. I mean any. Okay, as far as you can have the IP transmission, we can get there. And we put the MPEG transport stream on the IP network, and you will get there in zero latency compared with the broadcast TV, because the time for the IP signal at speed of light is 185 milliseconds around the world. Okay, that is much faster than go up to the satellite and coming back. So one thing, the most important thing is that we use advanced RTP, RTCP retransmission technology and method to make sure that retransmission and all the packet will arrive on time and not being impaired. We've been testing up to around 40 to 50% of random packet loss. So that means every 2 packets, you lost 1. Okay, that is extremely difficult. We've been working on it for many years to achieve that. We can streaming routed unicast to multicast, and then from multicast to routed unicast, because we are using RTP, so we do not need to repackaging it, or we do the multicast APR. So we just use the simple RTP sent out by the service router. That is what we build, the most important thing, over any IP network. I will show you the network diagram later on. So what we do is that the network element does the job. We focus on the network, okay, rather than content delivery. We focus on the network element, because that is the most important thing for the IP transmission. So what will be the benefit from that? We can do the fast channel change and the lowest latency, because we do not do the segmenting. We do not need to caching. There's no caching in the network, okay? Other than a few 1 to 2 GOP for the retransmission, and that's it. And master scalability, because we can use we multicast all the way to the edge, okay? For example, you want to multicast from Denver to Europe, you can create a tunneling, GLE tunneling, so you can use the PIN protocol independent multicast, stream all the way to Europe or Australia. We've been doing the testing already in Australia, in New Zealand, and Europe, and America. And we enhance the resilience of the packet loss and synchronized. All the devices are synchronized, okay? It's not like the HTTP streaming, TCP. Each element, the display player, can have different timestamp, and they play whatever they want. Using the MPEG transport stream, you have the synchronization by the MPEG layer transport. So every single device, they're synchronized. Just like the broadcast TV, okay? We just put the MPEG transport stream into the IP network and manage it. It's extremely sustainable because we reduce all the PC server in the data center. One of our customers done the calculation, 1 year of electricity bill in the data center can replace all the CapEx and OpEx in 1 year. So second year, you're printing money. So this diagram is empirical measured by our customer during the acceptance testing. Our starting up time is 19 milliseconds, the lowest, with a round-trip delay of 10 milliseconds. With higher round-trip delay, our startup time can be up to 350 milliseconds, up to 500 milliseconds. Between Europe and here, we have around 280 to 300 milliseconds of round-trip delay, so we go up to around 800 milliseconds for the starting up time. And then we compare with different technology, and they are far back. They're all different, okay? The broadcast TV around 2 seconds or 3 seconds, depends on the GOP size. And then all the HTTP streaming can be very low, but due to the head of line blocking, they're using TCP, so the starting up time can be random between 4 seconds to infinity, okay? Depends on whatever the TCP would like to do. And then we compare with the different technology. This is empirical measured with our customer during the acceptance testing. And everyone loved that because we try to measure the delay latency using time is very simple. From the stadium, we measure the time, and the player measure the time with time is, and then we just take the picture and snapshot, and then we measure the time delayed. In here, 95 seconds. It starts with very low. Some of the ultra low latency dash can be around 10 seconds delayed to start. But it can go up to 20 seconds, even sometimes 200 seconds. Okay, depends on the TCP timeout. This is called drift. If anyone going to tell you that the ultra low latency of dash can stay low, that guy must be telling you that he did that, or she did the testing in the lab under controlled environment. The network is perfect. If you have a packet loss, the head of line blocking will cause the latency every single time. And then until it just keep on drifting, I measured that with one of the Premier League, the football match. It's really funny because in the beginning it was only 10 seconds, 9 seconds to 10 second latency compared with the broadcast TV. End of the 90 minutes, it was around nearly 200 seconds delayed, okay. Case study, we compare with this one, use a global CDN, and that guy's in this room. And this is our solution from one of our customers. We are 67 seconds ahead of this global CDN. And then we compare with the satellite guy, and we are approximately 2 seconds ahead of the satellite. Reason is very simple. The satellite takes around 1.2 to 1.4 seconds go up to the geostation and back. Okay. And our solutions on the wire, fiber, is around 180 milliseconds to get there. Compare with the betting website. This is Canadian football. And we are approximately zero latency compared with a betting website. And actually, the betting website sometimes faster, sometimes slower, depends on how far they can push out, because they're still using HTTP push. Okay, how we have make this, okay, we have done it. The product solution, we use this standard and protocol. They are all standard, i.e. TF standard. So for the long distance streaming, we're using 2022-7. So we can stream from the stadium or from the video head end to the remote area with two stream, so or four or multiple streams. So make sure if one route fail, the other one take over. So that means if you have a network convergence, it's approximately 8-second outage, and we still have the one route still work. This is the network diagram over, and if you want to have the application node, you can scan the QR code. And in here, we take the MPEG transport feed in the peering point or video head end, and then we optimize the MPEG transport stream for IP delivery. Okay, if you do not optimize the MPEG transport stream for IP delivery, it can have all the nasty thing can happen. Okay, so what we've done is that we group all the I frame and B frame by frame type, and so we alignment with the audio, with the video iframe. Subsequently, we can start to decode soon after we receive the iframe and the audio packet. That is how we can get the 2-frame, 80 millisecond delayed to start the decoding. And then we send the multicast out all the way to the edge. Typically, it's in the BNG. BNG is the network border gateway. That is the first hop when you connect to the internet. So it's very, very close to your home. It's maximum 1 or 2 or 5 kilometers. Okay. And if you are not the BNG provider, we can use the CE router. We'll configure it as a CE router, so it's just behind the PE router, and then we can do the order streaming. We support different access network type. For example, mobile network RAN. Since a mobile network cannot support multicast or unicast, so most of the people using unicast using HTTP streaming, but we are using RTP streaming over the mobile RAN. Okay. And trace the pair or CMTS. CMTS has one simple big trouble, is that when you need to join the IGMP multicast, the CMTS can cause you around 7 to 15 seconds of IGMP join latency. So we have resolved this problem. How we resolve this is very simple. When we start to do the channel change on new representation, we burst at a slightly high bit rate, approximately 20% of the nominal bit rate, and then we go up and then wait for the iframe and the audio packet, because we already reorder it. And then we start immediately to decoding. It's always under 500 milliseconds, okay? Except when you're on the airplane, because I test on the airplane, it's around 1.2 to 1.5 seconds because the round trip delay to the MEO. It takes around 800 milliseconds to 1.2 seconds. And then it will burst until it fill up the buffer. So this fast channel change unicast duration is the purpose of that is to fill up the client decoder with MPEG decoder buffer. Is the encoder buffer, is the PTS minus PCR value. That is when we fill up the buffer, so we can let go and then do the IGMP join. If the IGMP join arrives immediately, we will say goodbye to the FCC server and then take on the multicast IGMP join. If any gap between, we use the retransmission to fill in the gap. So if the IGMP arrives approximately 15 seconds for the CMTS cable network, We will wait for the IGMP to arrive. Until it arrives, we let go. If the multicast does not arrive, we will forever unicast. And then you will ask, how the hell are we going to, how can we do the, sustain the scalability? Our surface router, the smallest one, is 3 terabit per chassis. The biggest one is 216 terabit per chassis. It's more than someone's CDN, the whole entire global CDN capacity, just one chassis. And the multicast, we can resolve as many as you wish. So the next question we ask, how can we backward compatible with the HTTP streaming or something else? So what we do is that we use a CDN in your pocket. Some of my colleagues tell me that we should call it RTP support TCP. Okay, I don't like it because we can offend a lot of TCP people in here. So if we call it CDN in your pocket, because we can put it into your mobile phone, and then we can put it in the pocket, and then walk around with the HTTP on the browser streaming. We will provide the client library as a container, and then someone will provide the rest of it. Okay, we will provide the information how to do the segmenting, because the segment itself going to be, we know the GOP, the iframe start, and the iframe next iframe. So this is the chunk segment. Okay. And then it can be in the home gateway with the Wi-Fi 7, so we can use it as on the OCI, Open Container Initiative. Or otherwise, you can put it on the mobile device or in the VMAX, depends where you want to put it, okay? And also this way, you cannot latch at all, because in your mobile phone, everyone knows who you are. And also we can use the app to limit the number of sessions, and subsequently you only can serve 1 session or 1 or 4 sessions per app simultaneously, and subsequently we stop all the latching. So, conclusion. Any question? I'm not going to read that.
Okay. One question, if you have one question. Okay.
You mentioned CDN in a pocket, and you know people who are deploying other techniques like multicast ABR,
yes.
They often discover that the gateways are not powerful enough.
Yes, we know.
So do you have experience to share on the population of gateway that support your technology?
First thing is that we do the development on the Raspberry Pi 2. It's less powerful than the home gateway. We developed and tested on the Raspberry Pi. We tested on the Raspberry Pi 2. It's very tiny. Our software only 300 kilobytes. If you limit the streaming capacity to 1 to 4 devices, you will resolve the problem. That's what we've done. We did the field trial in Spain in 2019, and then we shut it down in 2020 due to the pandemic. And we are starting up now again.
Okay, thank you. Let's thank our speaker.